Hey, welcome back to Fat Mama Physics. And these videos we are going to talk about power and efficiency. This video specifically, we are just going to talk about power. So let's do a quick coverage of power before we go into an example. Power. Well, think about it. You can do work very fast or very slowly. The rate at which you do work, that is called power. And what is that? We know that work is also equivalent to the change in energy in your system. So the rate of which your system changes its energy can also be called power as well. The shorter the time you use to convert one form of energy to another, the greater your power. Or the more energy that you convert in a specified amount of time, the more power your engine has. So what is the equation for power? So it can either be the work done per unit of time, or it can be the rate of your energy change per unit of time. And in terms of the units, it looks like joules per seconds, or we use watt. What's a watt? It's a watt, like the watts you see on your light bulb or the watt rating when you go buy light bulbs. That's the units we use for power. It is also a scalar quantity, so no directions, only a magnitude. Okay, so let's quickly get into an example, which is what I want to do here. Okay, example 1 is me, example 2 is you. So let's get started. The Serenity spaceship. Any of you have watched Firefly? Yeah, it stopped the seasons. It's unfortunate. Watch the movie though. The movie's awesome. Anyways, the Serenity spaceship, it has a mass of 54,000 kilograms, was cruising at 20 kilometers per hour when it saw enemy reaver ships not too far away. Before pulling a crazy Ivan to escape the reavers, whoosh, the pilot sped Serenity up to 100 kilometers per hour in 5 seconds. How much power output did Serenity spaceship generate? Haha. If you don't know what reavers are or what a crazy Ivan is, don't worry about that. You don't need to know that. You just need to know that Serenity went from 20 kilometers an hour to 100 kilometers an hour in 5 seconds. So let's do some labeling here. We got the mass. This looks like an initial velocity. This looks like a final velocity. This is our time. And we want to find power, which we know is work done per unit of time, or the rate of energy change per unit of time. It doesn't look like we have it looks like we can easily calculate the change in energy because the form of energy that we have that is changing, you are right, is the change in kinetic energy over time because the spaceship is speeding up. So we know that the change in kinetic energy is the final kinetic energy minus the initial kinetic energy, and that is just 1/2 mv final squared minus 1/2 Vmu squared, and I use V for final, U for initial, just like we use in your data booklet, all over time. Okay, so let's put in the numbers. We got the mass. Oh, right. Our velocities are in kilometers per hour. We need to convert that to meters per seconds. So let's do that here on the side here. We have the initial velocity is 20 kilometers per hour. We can do a conversion like the one that I'm showing you right now, which to get rid of the kilometers, we need to multiply by 1,000 meters per kilometer, as well as in 1 hour there are 3,600 seconds to get rid of the hours. Okay, hours here cancel, kilometer here cancels. So then essentially I am multiplying by 1,000 and dividing by 3,600. Let me teach you the shortcut, which this is essentially just 20 divided by 3.6. Why? This is if you move all the decimal places top and bottom, 1, 2, 3, 1, 2, 3, I get multiply 1 over 3.6, essentially just the same as dividing by 3.6 here. Okay, so I do that, 20 divided by 3.6, and I get 5.5 repeated, which then I need to make sure I save all those digits, meters per seconds. I'm going to do the same thing for the final velocity, but this time I am just going to divide by 3.6, which is much faster. I get 27.7 repeated, which then I'm going to make sure I save all those digits. in meters per second. Now I can finally put this into my power equation to solve for power. The time is 5 seconds, so I'm going to put that into... Okay, and putting into our calculator, I get 4 million. Aha, 4 million. With 2 sig figs, it's just going to be 4.0 times 10 to the power of 6, or 6 zeros. And our units, newly learned units in watts. That's a lot of watts. Too many questions there. Kidding. Okay, so now it is time for you to try example 2. But this time you got a space elevator. And oh, hey, it's being lifted. So we're not talking about speed. We're talking about some other form of energy. I wonder what that is. It's, there's your time. It's going up a constant speed. You don't have to worry about other forms of energy changing. Calculate the power generated by the space elevator thrust engine. So, good time to pause the video, and I will go over the solutions in fast play. First, we get the mass of our space elevator, which is 1,300 kilograms. We have the initial height of 0 because it's from the surface of the Earth. Final height is 780 meters, time as 2 seconds. So our power equation, we need the change in energy, which we only have potential energy changing here. No kinetic energy changing because our system is going at constant speed. The initial potential energy is 0, so it's just the final potential energy there, which is mgh final, 780 meters divided by the time 2 seconds, which then all of that gives us 5 million watts. Okay, here are our solutions, and we get a total value of 5 million watts, rounded up to 2 sig figs. So in this example, we looked at the change in potential energy instead of the change in kinetic energy. And since the elevator was going up at constant speed, there was no change in kinetic energy for you to also account for as well. So the only change in energy there was the potential energy. So very similar to the last question, except a different form of energy. Well then, thank you for watching this video with me, and hopefully you have a better understanding of power and can apply these skills to your practices and exercises. I wish you good luck, and Fat Mama Physics signing out.